ये देखना यूट्यूब पे आ रहा है क्या? यूट्यूब पे मेरा वाला ये वीडियो आ रहा है क्या लाइव? ये आवाज़ फिर इसमें जा रही होगी। ईयरफोन लगा लो ना। today we will talk about the course. Already you know that the applied physics. This is the tutorial class of applied physics. This is on NPTEL. So here we are some live interaction. Whatever you did not understand during the class, you can ask in this session. So in the last week, which is week 6, so you have been seeing that these three topics sir has covered in this week. So very quickly I will go through all these uh, derivations, and then we will go to the our tutorial, which is of last week tutorial 5. Okay, so as you see, sir have discussed this multiple beam interference. Okay, so what is this multiple beam interference? As you know that so far sir already discussed the many interference theory we have seen. So in that one we consider that light is coming from two different places and interfere at some place. So here we observe some interference fringes. Okay, so there are some circumstances which can in the single ray diffraction. For example, if we take some mirrors, okay, light is coming on this mirror, we called it E0, and light will go through the transition of this one, okay, and then it again reflection, again transition, and again reflection, and again transition, like that. So light will also transmit through in this region, light will go transition in this region and this region. So this is our reflected ray. Let's see. So if this the amplitude of this one is E0, then let's the reflectivity and transmission of this coefficient of this mirror is R and T. Then what, and on this one R dash and T dash. Okay, and the refractive index we are considering here is N2, and the refractive index of a film or mirror between in this region, and here is N1. So we consider N1 equal to N2. Okay, and R is equal to R dash and T equal to T dash. Okay, so not we are not considering here for now, and we will see later. So this ray is first time reflected ray, this is second time reflected, and this is third time reflected. So all these, if we consider here some mirror, so all these will come at point P, will be in coherence. Okay, so if it will be R and T, फिर से बोलना, ओके सो ठीक है, मैं रिकॉर्ड कर ले रहा हूँ, रिकॉर्ड वाली वीडियो अपलोड कर दूँगा. So as we know that here this is R into R dash. So this ray is going to this region. This will be E0 into R. Sorry, this will be E0 into R, and this will be E0 into T. From T or from this one, then here it will be E0 R, and here it will be E0 T into R, and here it will be E0 T square, sorry, T dash into T into R dash. Okay, so something like that. So you can consider the light will come here E0 into T, then E0 T so here will be E0 T into R dash, because this reflected here, so R dash will be multiplied, and then here will be R dash T and T dash. Okay, the second ray will be this one, and the third one, then here it will come E0, there will be T, then R dash is square, because R dash will be R dash here, R dash is square into T. Okay, and then this ray will come here E0 R dash T, and R dash 4, sorry, this will be R dash 3, R dash 3 into T, and from here it will be E0 R dash R dash 3 into T, and T dash. Okay, so if we add all the resultant, the fourth one, it will be something like whatever reflected electric field, reflected amplitude at point P. So we can write it like E0 R will be E0 into R, the first one, and minus E0 TR T dash plus E0 TR cube T dash, and plus E0 R5 T and T dash, plus similarly it will go for the infinite one. So or we can write here like E0 R will be E0 into R minus E0 T T dash into R. If we take common, then it will be 1 plus R square plus R to power 4 plus dot dot dot. Okay, so if we consider that R is less than 1, so literally R square will also be less than 1, means then E0 R will be E0 R minus, this will be our A term, E0 t t dash r, and this will be 1 upon 1 minus r square. Okay, so when we consider that Stokes treatment of the principle of reversibility, so that the t dash is somewhat equal to 1 minus r square. It means here e0 r will be equal to 0. Okay, so like we have here some assumption. For example, if let's consider that two consecutive wave this way, here to here, the path difference can be considered is equal to, if the distance is t, then 2 and d. Okay, it will be 2 and d cos theta. If we consider the angle of incidence is theta, then it will be 2d cos theta I. And if this lambda equal to m, this difference will be n lambda, then what will happen, then the second, third and fourth and successive waves will all be in parallel at point p, parallel and in phase p. The wave which is e1r, which is denoted by here, however, because of its reflection at the top surface of the film, will be out of phase by 180. Okay, so with respect to all other waves, okay, so the phase shift is embodied in the fact that r, we are considering r equal to minus r dash. Okay, and r dash occurs only in odd powers. Okay, that's why here we are considering r dash power 3 and so on like that. Okay, so the sum of scalar amplitude should be like that. Now when this omega is equal to m lambda, and also the second, third and successive waves exactly cancel the first reflected, it means if this will happen, means the third, fourth reflection will cancel out the first reflection. Okay, so what will happen, then the first reflected wave, as we can see in this one, so in this case the no light is reflected. Okay, no light is reflected, all the incoming energy is transmitted. Okay, so all the incoming intensity will transmitted. And the second special case arises when we consider that this lambda is, sorry, this lambda is equal to m plus half lambda. Okay, means odd multiple of lambda. So when the two first and second rays are in phase, and and the other adjacent wave are lambda by 2 out of phase, then that is the second is out of phase with the third is out of phase with the fourth, and so on. So the resultant will be e0r, it will be like e0r plus e0, it will be e0 tr t dash minus, it will be e0 tr cube t dash, similarly e0 tr power t dash minus, like that, because these two will be out of phase, this and next one will be out of phase, this will be out of phase. Okay, then e0r will be e0r plus e0r t dash, if we take common, then 1 minus r square plus r to the power 4 minus dot dot dot. Okay, so this will be e0 r equal to e0 r, if we take common, then 1 minus this will be t dash y 1 plus r square. Okay, because now then if we consider this t into t dash equal to 1 minus r square, so this will be e0 r equal to 2r divided by 1 plus r square e0. How we can derive this? This 1 minus r square upon 1 plus r square, there will be 1 plus r square minus 1 plus r square divided by 1 plus r square. So 1 to 1, then 2r square will be there. Here will be 2r square. So since the particular arrangement results in the addition of the first second waves which have exactly large amplitudes, it should yield a large reflected flux density. So the radiance is proportional to, then the irradiance if we find, so it will be, irradiance will be e0 r square by 2. It means it will be e naught square by 2, and of this square it will be 4r square by 1 plus r square का whole square. Okay, so this is the case when the irradiance will be like that. So we will now consider the problem of multiple beam interference in more general fashion, making use of complex representation. Okay, again let this n1 equal to n2, then thereby avoiding the need to each interface, the optical field at point P will be given by, so the optical field at point P are given by something e1r, it will be e0 r e to the power I omega t, let's consider, and then e2r it will be e0 t r dash t dash e to the power I omega t minus delta. Similarly e3r vector, it will be something like e0 t r dash q t dash e to the power I omega t minus 2 delta. Okay, and so on. And if we consider nth time reflected wave, it will be something like e0 t r dash to power 2n minus 3 t dash and e to the power I omega t minus n minus 1 into delta. Okay, so this will be your nth reflected waves amplitude. Okay, so now e0 e to the I, where we are considering e incident is equal to e0 e to the power I omega t. This will be our incident light. Then the term delta, this delta, 2 delta, that dash n minus 1 delta are the contributions to the phase arising from an optical path length difference between the adjacent ray. Okay, so this ray, this delta will be in form of k0 into path length. This is path length, this delta is path length. So there is a additional phase contribution arising from optical distance traversed in reaching point P, but this is common to each ray, okay, and has been omitted here. So the relative phase shift undergone by the first ray as results of the reflection is embedded in the quantity r dash. So we can write the resultant electric field or optical contribution. This will be something E1R plus E2R plus E3R dot E and R. Okay, so now can we substitute this? Yes, we can substitute this with the quantity that E1R is equal to ER e to the power I omega t. Similarly, E0 R dash t t dash e to the power I omega t minus delta. Similarly, so on. We all have replaced these things. So this is again a series, so we can write it like E0 R E0 R e to the E0 e to the power I omega t, and we can write it R plus t t dash R dash e to the power minus I delta. Okay, and this will be common, and this will be 1 plus R dash square e to the power minus I delta. Okay, sorry, and plus R dash square e to the power I delta का whole square and so on. Okay, so if we consider that R dash square e to the power I delta is less than 1, and then we will find this ER, it should be written like E0 e to the power I omega t. This is R plus R dash t dash e to the power I delta minus I delta divided by 1 minus R dash square e to the power I minus I delta. Okay, so in the case of zero absorption, no energy being taken out of the wave, so we can use the relation that R is equal to R dash and t dash is equal to 1 minus R square. Okay, so if we put these two relation in this one, then we will find this ER resultant wave will be E0 e to the power I omega t R1 minus e to the power minus I delta upon 1 minus R square e to the power minus I delta. Okay, where delta is your phase change. So the reflected flux hence can be contributed that IR equal to ER dash star divided by 2, so it will be E0 square R square 1 minus e to the power minus I delta and 1 minus e to the power I delta divided by 2 1 minus R square e to the power minus I delta and 1 minus R square e to the power I delta. Okay, So it can be transformed into IR is equal to II incident irradiance into 2r square 1 minus cos delta divided by 1 plus r to the power 4 minus 2r square cos delta. Okay, so this will be the radiance due to the multiple beam interference. So where this I is equal to represent E0 square by 2, which is incident irradiance. Okay, so similarly we can also calculate the transmitted wave amplitude. Okay, so this leads to the interference per term. How? So let's consider this transmitted wave as this can be calculated similarly. I am not going into the derivation, so it will come something like 1 divided by 1 plus 2r divided by 1 minus r square and sine square delta by 2. Okay, and also this IT is will come in the above form like IITT dash square divided by 1 plus r to power 4 minus 2r square cos delta. Okay, so this so the total transmitted flux density emerging from the film. So I incident will be IR plus IT, because we are considering there is no absorption. Okay, so what is the IT max? So IT max will be when cos delta will be 1. Okay, and it is minimum when it is minus 1. So IT max, if cos delta is equal to 1, when cos delta is equal to 1, then this d is equal to 2 pi m. Okay, so IT max will be equal to I incident. Okay, all the light coming to the go to the transition, not in the reflection, and in the same condition IR minimum will be 0. Okay, so this can be calculated from this formula. Okay, so as we would expect from this equation, hello, hello, yes, okay, okay. Then if we have this case that cos delta is equal to 2m plus 1 into pi, sorry, this delta is 2m plus 1 pi, then I T will be transmission will be minimum, and this will be equal to IR 1 minus R square whole square divided by 1 plus R square का whole square. Like if you consider here delta is equal to cos delta is equal to minus 1, then it will be plus, and this will be 1 plus R square का whole square, and this T dash is equal to 1 minus R square. Okay, then the correspondent IR maximum, it will be equal to I incident into 4R square divided by 1 plus R square whole square. Okay, so notice that the constant inclination fringes pattern has its maximum. Here we are not changing constant inclination, has the maximum when delta is equal to 2m plus 1 into pi, means 4 pi nf divided by lambda 0, this d cos theta I, it will be equal to 2m plus 1 into pi. Okay, so which is the same result as we had previously. Okay, so now we can introduce one quantity, that is coefficient of fineness. Okay, so coefficient of fineness will be defined by the equation with IR and IT, that this for coefficient of fineness F is equivalent to 2R by 1 minus R square t power square. Okay, so where these equation can be written as IR by II is equal to F sin square delta by 2 divided by 1 plus F sin square delta by 2, and IT by IE, it will be 1 by 1 plus F sin square delta by 2. So this term this term 1 plus F sin square delta by 2 is, we are considering here a theta. This is known as Airy function. Okay, so it represents the transmitted flux density distribution and is plotted will be like let's consider here delta and here IR divided by II. So it will be something like that. Okay, so this will be when F is 200. If F is 100, let's say, so it will be something like, okay, similarly if F is equal to 2, then it will be like that. Okay, so this is called array function, and the complementary function, that is 1 minus F, it is plotted here. So from the same formulation we can go for the Fabry-Perot interferometer. Okay, so the multiple beam interferometer first constructed by Charles Fabry and Alfred Perot in late 1800 is the considerable contemporary interest. Besides being a spectroscopic device of extremely high resolving power, so it serves as a basic laser resonant cavity. Okay, so in principle the device consists of two parallel planes, okay, highly reflecting surface separated by some distance d. So this is simplest configuration, and as well as C other forms are also badly in use. Okay, so in practice two semi-silvered or aluminized glass optical flats form the reflecting boundaries. Okay, so they enclosed air gap generally range from several millimeter to several centimeter. When the upper apparatus is used interferometrically and often to considerably greater lengths when it serves as a laser resonant cavity. So now the this is the interferometer. So the next terms are also used, Italian. Okay, so what is the difference between Italian and the interferometer? So generally both can in some sense are the same phenomena, that is interference, but in Italian mostly the mirror are placed hinged and at the constant point, then path difference can be changed by the rotating the mirror. While in interferometer there are two mirror and they are moved and the separation d is changes, so this is called interferometer. While in this case this d is fixed and this is only rotated, not moved. This is rotated like that. Okay, to introduce the path difference. So this is the main difference between Italian as well as the interferometer. So let's consider two partially mirror. Okay, so we have relation t dash is equal to 1 minus r square and t plus r equal to 1. So now we consider t plus r plus a equal to 1, not t equal to 1. Okay, so one further complication introduced by metallic films is an additional phase shift is comes here. It depends on incident angle theta. Okay, either 0 or pi, the phase difference between two successive transition then can be written as delta is equal to 4 pi nf by lambda 0 d cos theta I. Okay, plus 2 phi. So for the present condition this theta is small and phi may be considered to be constant. So in general this d is also large. So this lambda 0 so small that phi can be neglected. Okay, so then we can write it over I equal to t square 1 plus r square minus 2r cos delta. okay, where this T is transmission, R is reflection coefficient. So, or equivalently we can write IT equal to I equal to T by 1 minus R का whole square, and in this one we can write 1 plus 4R upon 1 minus R square sin square delta by 2. Okay, so making use of the equation A plus R plus T is equal to 1, the definition of the array function can be obtained that IT upon I equal to 1 minus A divided by 1 minus R whole square into A theta. This is a array function. So as compared when the zero absorption, this term will be 1 and this will be equal to A theta. Okay, so the peak transmission is defined as IT max divided by I. This will be equal to somewhere 1 minus A upon 1 minus R का whole square. Okay, so this the measure of the sharpness of the fringe, that is how repeatedly the radiance drops off on either side of the maxima, is given by the half width. Okay, this is the gamma. So like for example, this is your delta and this is your IT upon IT max. So this will be, sorry, this will be like that. So this is known as gamma, which is half full width half maxima. Okay, so when IT equal to IT max by 2, this will be IT max by 2. So this length is a gamma. So from here we can say this gamma is somewhat comes in the term of 4 by root f. Okay, so this f so something like this formulation comes in the derivation. Okay, so this is something sir maybe have derived in this class, and now I am going to solve the tutorial. So in this tutorial we have 10 questions. We will solve one by one. So question number 1 is, if optical path length difference between two waves is m plus half lambda where m is 0, 1, 2 like that. So our option is constructive interference. Number 2 is destructive interference. Number 3 is interference pattern will not be observed. Fourth one is none of these. So the correct answer will be, because this path is lambda by 2 means this will be destructive interference. So our right answer will be destructive interference. So next question, the question number 2. When a monochromatic light wave is incident on a thin film, comma, it splits into reflected and refracted light. The correct statement, so the correct statement, so we have that this amplitude and frequency both will be same. B is amplitude and frequency. Amplitude will be same and frequency will be different. In third option, C, this amplitude will be different and frequency will be same. And option D is amplitude and frequency both is different. So as we know, when this light will be half reflected, half transmitted, means this amplitude will be different while this frequency will be always same. Okay, so our option will be C. Question 3 is the shape of wavefront emitted from point source will be, so it will be spherical, B cylindrical, C is plane, D is conical. Shape of wavefront emitted from point source. So point source will be always spherical. Our next question, question number 4. If a thin film is kept in air then condition of interference minima for two reflected waves will be. Your options are m plus half lambda, m plus 1 by 4 lambda, m plus 1 by 8 lambda, and D is m lambda. So as you know, this is your film. So these two waves have the interference of minima is, the condition will be 2 and d cos theta will be the path difference between these two waves. Okay, and the additional path, the difference will be pi by 2, which will be corresponding to lambda by 2. This will be m plus half lambda. Okay, so it will be m plus half lambda means m plus 1 lambda is equal to m lambda. There will be the your answer. Similarly, question number 5. Central spot in Newton's ring would be. So your answer is dark, B is bright, C depends upon refractive index of lens, and depends upon the thickness of lens. So as you know, the central part, when is the equal part difference will be coming. Okay, so equal part difference means there is a lambda by 2 difference, so always the spot will be dark. Sorry. Okay, question 6 is working principle of Michelson interferometer is based upon of which one? Division of wavefront, division of amplitude, or Huygens theory, or Newton's coscalar theory. So it is always division of amplitude. Okay, so answer is division of amplitude. Question 7 is, if the separation between two mirrors is increased in Michelson experiment setup, then the ring radius of the fringe pattern is increased or decreased? If separation of two mirror increased, Michelson interferometer, then the ring radius of fringes will be increased, decreased. C is remains same. D is none of these. Question 8 is, if the separation between mirror in Newton's ring experiment for higher order fringe spacing between two consecutive fringes is reduced, separation between two consecutive fringes reduced. B, separation between two consecutive fringes increase. C, spacing between two consecutive fringes remains same. Irrespective of order of fringes. So question 9 is, in typical Michelson interferometer, the light incident wavelength lambda is 532 is used if one finds 500 fringes are disappeared on moving the mirror, the shift in the mirror position will be. So we have to find shift of the mirror. And the question number 10 is, convex lens is there, rests on a optical flat in dust free Newton's ring setup in air. So it's illuminated by a light of 532. Okay, 532. If the radius of curvature of the lens R is 20 centimeter, then how far from its central fringe will we if we find the 20th bright fringe? So we have to find the separation, the distance of 20th bright fringe. Okay, so these are the questions. So we will discuss one by one. So in Michelson interferometer, we have that a shift, the shift in path of lambda 0 by 2 corresponds the apparatus is in air to a shift of OPL of lambda 2. So this will we have 2D so the optical path length, how can we consider? The mirror shift is, let's say, D, then optical path length will be n into D. Okay, where n here. Okay, so this will be the optical path length. So this optical path length, it should be n into lambda 0. So we have to find the change in delta D. So that is this is D's change in position. Okay, so this D will be n into lambda 0, means n, the 500 fringes have moved, so it will be 532 nanometer. So it will be 5 2 ja 0 and 5 3 ja 15, 116, 5 5 ja 25, this is 26 nanometer. It will be 266 micrometer, means 0.26 mm. Okay, so this will be your answer. Similarly, the Michelson interferometer, if you have read, then we know that the center of exit fringe, it will be m plus half lambda into radius of curvature r to power 1 by 2. Okay, so we have this x m dash is equal to m dash minus half lambda into r to power half. We know this m dash is equal to 10, no sorry, here is 20. Okay, so if we put this all, x m dash is equal to this will be 20, this is 20 minus half is 19.5 into 532, and radius of curvature is 20 power half. So it will come, this is in nanometer, so answer will be something like what, just calculate it, you will solve. Okay, so now in Newton's ring experiment, for high order fringes, the fringe width will, separation of fringes is decreased. Okay, it will reduce, and if separation of two mirror increased in Michelson interferometer, then what will happen? Fringes will increase or decrease? Fringes will be decreased. Okay, so this is all the things we have for today. We will meet in next class. Thank you.